Now, my dear students, we are heading towards the properties of the Laplace transform, and in this lecture we will know about the basic properties of Laplace transform. Here is a chart of Laplace transform with the properties that the property that it governs. So in linearity property, it has a linearity property. Here you can see, you can just after Laplace transform, the thing is quite similar, and the ROC is an intersection. The time domain shifting, that means that will just e to the power minus st naught. It's quite similar to the Fourier transform series, Fourier transforms. Here you can see the time shifting t naught is just is the power of the e to the power and xs. Laplace domain shifting e to the power s naught t, same as Fourier transform. Just here you can use s against the omega. Nothing will change. And this is the ROC, that is the ROC R. Here is R plus real part of s naught. Time and frequency domain scaling similar as 1 by a x s by a. Conjugations are quite similar. They both are the conjugates, the transform and the S-plane. The time domain convolution, that is also similar to the Fourier transform, that is multiply with each other, and ROC is between them, so the intersection part. Time domain differentiation, ddt of xt, and you know the ddt in Fourier transform we probably use j omega, but here we use s after transforming, and xs, this xt will be transformed as xs, capital xs. Laplace domain differentiation, that's minus txt, that will be dds of xs. That means at t, the time in the time domain is probably the differentiation with respect to differentiation of with x with s in the Laplace domain, and the time domain integration is minus infinity to t, so x tau d tau, so that will be 1 by s. Integration is 1 by s, differentiation is s. That means where do you get the differential values, that is denoted as s, and where do you use the integration, that is 1 by s. And there is initial value theorem, there is a final value theorem, quite similar to that we have learned before in the Fourier transform part. There are some Laplace transform pairs, the usual pairs that we have to know to solve some mathematics. Delta t, ut, delta t is 1, that's unit impulse, ut, so that's 1 by s, minus u minus t 1 by s, t to the power n ut, that is n factorial divided by sn plus 1. That means if you use just like that, t square t square ut, if somebody say that is t square ut, and you have to make the Laplace transform, so probably what you do after Laplace transform, the thing t square, that is the minus t square, and t square 2 means 2 factorial divided by s to the power 2 plus 1. And that means 2 factorial means 1 into 2 multiply 1 multiply 2 with the s cube. From that we can use these equations to e to the power minus at, that is the equation. So that is the pairs that you usually use. That is the cos omega t, you can get this. So that is the unit function, unit impulse function, that is the impulse function. So this kind of things are quite common to it. So you should know about the ROC and the transform pairs to understand the clearly and use in mathematics. In linearity, that quite supports the linearity property. That means whether you use transformation, you get each of the transformation in the plus sign, and the ROC